Zig has many different ways of allocating memory. The default way of allocating memory is by using this general purpose allocator. And this is one of the advantages over a legacy programming language like C, 40 plus years old. It has lots of footguns and lots of security holes that are easy to create. If you look at the way the allocator works, though, in the case of the general purpose allocator, whenever you need memory, you ask the allocator. You can create more complex structures, and then you can use strings and arrays that grow, and then everything is explicit about who owns the memory, and the temporary allocators are for short-lived memory, and then finally at the very end you have no hidden allocations. You have to handle allocation errors with try, defer ensures cleanup, and the memory ownership is always very clear, and you also can detect leaks at runtime. This is safer than C because you don't have to think about, oh wait, I forgot to free something, to free a pointer. You forget about some of the things you've done previously. But if we get into the details and explain now how memory management is different from C and Zig to Rust and Zig, Rust has something called ownership and borrowing. And the idea here is that you have to always declare the ownership. And when you borrow something, you have to explicitly have a control. And this allows you to drop things automatically. With Zig, it's an explicit allocator. And with an explicit allocator, you have to actually explicitly at the end deallocate it. Some of the big differences as well are that with Rust, there are compile time checks. So it'll let you know, hey, you can't do that. You can't move this particular variable. You have ownership of it, etc. With Zig, though, it's manual, but it's also explicit. So it's not accidental. At the very end of using the general purpose allocator, you would actually go through here and essentially call the deallocation so that you know that you're done. Also with Rust, there's mutability. So in Rust, you have to explicitly say whether something's mutable or immutable. Zig, you have the ability to do runtime mutability. So the big difference between Rust and Zig is that the ownership rules are enforced at compile time. There's a single owner for each piece of memory, and the borrowing rules prevent the data races, and the memory is freed automatically. So it's essentially safety is built into the language, but you pay a little bit of a performance price for that. With Zig, you have explicit allocators that have to be passed around. The memory management is used with defer. There are no compile time ownership restrictions, and the runtime, though, will check for leaks and errors. Now, if we get into the core philosophy of Rust, it prevents memory errors at compile time, which as a general purpose programming language is really nice. On the other hand, Zig says, I want to make memory management explicit and transparent, and I want to catch errors at runtime. Now, if we look at how this plays out, another way to think about this would be to think about in the general case of the allocators, so the general purpose or the normal allocator that you use most of the time with Zig, you can think of it as a toy box where you have to put back all of your toys. And if you run at the very end, the allocator .free, so defer allocator .free, put the toys back here, it'll actually tell you, hey, wait a second, I was able to, when I run gpa.dinit at the very end, there's something wrong. Like you didn't deallocate everything. So you actually have, again, this toy box concept where you take the toys back, and if there's one missing, we're able to say, oh, wait, that's right, I left something out there. Now, there's more that you can think about beyond just the general purpose allocator, though. So let's dive into 4 of the types of general purpose allocators or memory allocators that are available. The general purpose allocator GPA tracks all the allocations. It detects the leaks. It does double freeze. So this is most of the time what people would use with Zig if they want that granular control. There also is arena allocator. And the reason for this would be you want all the memory freed all at once, and you want very fast allocations. So this would be good for temporary data. And if you look at a third option, we have fixed buffer allocator. So this would be stack memory only, no heap allocation. So if you're building an embedded system, for example, this could be a great way to build it. You know exactly the allocation that you can use, and you have to fit things with inside of that. Finally, we have page allocator, and this is direct OS memory, and it has page aligned blocks, and this would be best for really large applications. So let's go ahead and talk about how this works then. So in the case of the general purpose allocator, this is like a librarian tracking books. This is just a regular program. The arena allocator, this is like dumping Legos. You want to clean them all at once. This is best for parsing JSON, for example. A fixed buffer allocator, this would be like a fixed size box, again, like an embedded system. And then a page allocator, this is like buying land, like you want to buy a huge chunk of land and then you split it up into a housing tract, etc. So really the rules are GPA is careful tracking, arena is throw away everything, fixed is it never grows, and page is big chunks only. So in a nutshell, let's look at some of the real world implications of this. If you're comparing it, for example, to Rust, in the case of the general purpose allocator, you could have an 800 kilobyte static binary. With Rust, maybe it's 2.8 megabyte static binary. So the advantage here in the case of Zig would be smaller runtime, no mandatory allocator. In the case of the arena allocator, with Zig, you get to choose your allocator. With Rust, you always have to include the memory safety runtime. So the advantage here would be for an embedded system or something else, you have optional runtime overhead. In the case of the fixed buffer allocator, one of the things that you could do would be to have zero runtime overhead. Also, Rust could include error handling runtime. So again, if you are thinking about embedded systems, maybe you don't want that runtime overhead because you know what you're doing. And then in the case of a page allocator, this would be like direct OS calls. And then with Rust, it would be an abstraction through a standard library. So the big differences here are the zero abstraction cost. So in terms of the binary size, if we wrap everything up here, Zig, maybe a hello world is 300 kilobytes, Rust 1.8 megabytes. For memory usage, explicit, there's no hidden allocations. With Rust, it's possible you have some hidden stack protections. In terms of startup time with Zig, near instant, the runtime size maybe would be 3 kilobytes. With Rust, you have to initialize a runtime. The runtime size could be maybe 100 kilobytes. And in terms of things like Docker, this could really play a role depending on what it is you're doing. Let's say you wanted to build a minimal HTTP server. With Zig, it could potentially be inside of Docker. With Alpine, it could be 300 kilobytes. And if you build into Scratch, for example, with Rust, that minimal HTTP server, it could be maybe 2 megabytes. So that's a pretty significant difference depending on what it is you're building. That could make a difference in an embedded system. So in the real world as well, if we look at things like, let's say JSON and SQLite, a Zig server could be 850 kilobytes, a Rust server could be 4.2 megabytes. So in a nutshell, I think the idea here is that if you're already bought into Rust, you might also think about Zig for some of these specialized use cases. I guess the way to think about it is if you're already into using a power drill, maybe you also want to use maybe like a power tool to cut the wood, or you want this specialized tool to allow you to do really advanced things. So Zig has some very interesting characteristics, and memory is one of the places where you can really see those characteristics shine.